Hello, everyone, and welcome to this presentation of a FACT 2023 paper titled The Possibility of Fairness, Revisiting the Impossibility Theorem in Practice. And as you can see, we have quite a long list of authors here, and most of us are from NYU, but I just wanted to point out that two of the authors, Nazar and Tanya, were actually part of the NYU Responsible AI Summer Research Program that occurred with Ukraine in 2022. And you can read more about this program at this link here, but I just wanted to give a special shout out to them who worked on this project in the midst of the war going on in Ukraine and really made amazing efforts. And so to jump into the paper, we'll start with the background and motivation. So it's probably no surprise to the audience of this presentation that over the past dozen years or so of research in algorithmic fairness, researchers have defined many different ways to measure fairness of predictive algorithms. And some of these might be terms you're familiar with, like equalized odds, disparate impact, or perhaps like the false negative rate or false positive rate disparity of an algorithm. And what's kind of been revealed over time, that given all of these different metrics, these dozens of different metrics, is that fairness is highly context dependent. And there's many contexts where we might want parity between, one of these metrics or even multiple of these metrics. And what is fair in one context might not actually be fair in another context, and generally involves conversations with stakeholders or communities that are affected by algorithms. And so as an example, one could imagine that for a certain predictive algorithm, it's important to have both demographic parity, i.e. balancing the representation of an algorithm, and the equal false negative rates, that is balancing a certain type of error rate. These might both be relevant for a particular algorithm. And kind of as a result of talking about these fairness metrics and which can be applied, researchers have actually uncovered that there's incompatibilities or kind of like theoretical limits between these metrics. So Kleinberg et al. Found that one cannot simultaneously equalize calibration within groups and the balance for the positive and negative classes outside of two special cases. And these are if there's equal prevalence, also called base rates, equal prevalences between groups. So suppose you have a majority and a minority group, that would mean that they both have to have the same rates of the outcome being predicted. Or the other case is that there's perfect prediction, if you have an absolutely perfect predictor. But outside of these two very, very rare cases, it's impossible to equalize this set of metrics. Kaldakova defined a near equivalent result in classification as the relationship between the false positive rate, the prevalence, the precision, or PPV, and the false negative rate of a classifier. And most recently, Su et al. In 2023 defined it as simultaneously satisfying equalized odds and demographic parity for any classifier. Now, importantly, these are all mathematical results that cannot be argued. These are limits that on what you can actually satisfy, theoretical limits on what sets of metrics can and can't be satisfied. But it's becoming more and more obvious that theory does not always equal practice. So there's actually an increasing number of studies in fair ML literature, showing this. And one example is a recent publication from Rodolfo et al. On machine intelligence that showed that it's not always necessary to sacrifice accuracy to ensure fairness, which goes a little bit against the conventional wisdom of theory. And there's many different reasons for this, but one of the main reasons is that practitioners often take a different lens than those that are creating theoretical results. And so one example is that it's not always necessary to ensure exact parity between metrics, but instead to allow some kind of margin of error. And so Kleinberg et al. Did investigate these approximate fairness constraints, but importantly, they did not explore the space of solutions under epsilon approximate relaxations, nor did they detail the implications that these relaxations might have for practitioners. And so as a motivating example, we present a bit of a thought experiment. So in the field of education, the racial achievement gap is one of the most pervasive examples of systemic disparities that have been present, since for at least 20 years or 25 years since they've been measured. And this is the racial achievement gap is this idea that black and brown students tend to graduate at a rate that is 10% less than their white peers. And so the idea here is, how do we think about this base rate difference of 10% when we're trying to build models for predicting performance that satisfy seemingly incompatible fairness metrics? So if we're in a context where we should be satisfying false positive rate, false negative rate, and precision parity, if we allow some kind of margin of error, how meaningful is this 10% difference? And this is really what this paper sought to explore. And we do this by defining something that is known as the fairness region. And I'm going to go through some of our analyses in this paper, but our paper is actually very dense, and so I have to skip over a lot of details and just kind of offer a high-level presentation. But I strongly encourage you to check the paper and to dive deeper into some of those details if that's something that you're interested in. So we began by encoding approximate fairness constraints. And this is done very simply by reparameterizing the impossibility theorem defined by Kaldakova that you saw in some previous slides, where we add relaxations for each parameter. So rather than saying that the precision of group 1 must equal precision of group 2, we allow some kind of epsilon difference between these. And by doing this, we're able to afford us a space of solutions, wherein each solution represents a potential classifier that balances all three metrics within our desired tolerance. And so what this looks like is by going through, by adding these relaxation parameters and solving for the false negative rate of one group, we're able to get this expression below, which looks at first glance pretty intimidating. But one of the things that we point out is that this is actually really mostly known, fixed or known parameters from the data set, or predefined a priori. So for example, all of the epsilon tolerances are something that are able to be predefined ahead of time, and then the prevalence and the prevalence difference comes directly from the data set. And by kind of sweeping over these different options for the epsilon values, we can create a fairness region. So this is for a prevalence difference here of 20% between two groups, and allowing the epsilon difference to be between minus 0.05 and 0.05. And you can see that this results in a rather large fairness region. And importantly, each point in this fairness region, or each point that we're discovering in the fairness region, represents a feasible model that's satisfying our approximate fairness constraints. And what's really great when we use this relationship is that we can actually define a clean expression for the area of a fairness region. But there's one really important detail here, which is that this analysis was done for an alternate impossibility result that relates the false positive rate, the false negative rate, and the accuracy of a classifier. And this is explained a bit in the paper, but the reason that we did this is that unfortunately when you move to the false negative rate, false positive rate, and precision, it is ripe with nonlinearities, and it becomes much more difficult to find a closed form solution. But we didn't want to give up there because we know that precision is much more important metric than accuracy when it comes to actually working with these, to working with these types of metrics for practitioners. And so what we actually did is we implemented a constraint program that does a similar type of analysis, but that relates the false positive rate, the false negative rate, and the precision, and allows us to input some type of margin of error, and we can actually count the number of solutions that are found. And so on the left here, this is the result when we allow no margin of error difference between the metrics. And as expected, there's only feasible solutions to satisfying all three fairness constraints when the prevalences between the groups are exactly equal. So on the y-axis, we have the group 1 prevalence, and on the x-axis, they have the group 2 prevalence. And here we have the sum of the total number of solutions. But by allowing just a 5% difference between these metrics, we actually have, you can see the space of solutions is much denser, and there's actually 10 times the number of solutions just by adding, like I said, a 5% margin of error. So this gives us some pretty promising results that slight relaxations in fairness constraints can actually lead to an abundance of solutions. And so we also ran some experiments on real-world data sets, and we did this by creating a linear program that takes in a data set, a resource constraint, a set of fairness constraints, a classifier, and a range of the performance on that classifier. And it's able to ask the question, does there exist a set of k observations for which all three fairness constraints are satisfied and the precision of the classifier is not reduced? And the reason we do this experiment is if this is the case, then then there must exist a model that could actually identify this set of k observations. So trivially, you could think of using the index as the labels for creating a function that just maps from the index to that set. We used 5 different data sets, which are listed here. One really interesting data set is the Ukrainian External Independent Evaluation data set, which if you want more information, just shoot me an email or anyone on the team, and we'd be happy to talk more about it. And so this is an example output of that linear program. And so what you can see here is on the top, this is looking at the precision and the recall of the classifier. And so over different ranges of k on the x-axis. And so what we're seeing with the red dotted line and the blue dotted line are the kind of the unconstrained values if we didn't have any fairness constraint. And so the red line, which is those that are fairness constrained, you can see that it only starts to deviate when we hit about k equals 15. And on the bottom here, this are the fairness constraints and the disparity, and anything that is within these dashed gray lines is considered fair to the 5% measure on all of these metrics. So you can see that as long as we're less than k than 15, we have a classifier that's not trading off any precision or recall, and that is fair within all 3 of these constraints. And so overall, this is kind of just one example of one of these outputs, but overall our findings on all 5 data sets show that our experimental results corroborate our theoretical findings. And so there's also a tool that we've created that you can use to run this type of analysis on your own data set. So as I said earlier, our paper is really dense and there's a lot of theory. And so we actually choose to frame the discussion in a more practical way as guidance for practitioners. And so one of the things that we talk about is this kind of margin of error analysis, which is given a margin of error between metrics. So for example, a 5% difference, we find that the size of the fairness region, or what you could expect for your fairness region, is affected by these 4 factors. So the group prevalence values, for example, how close they are to 50%. The size of the prevalence difference, the classifier performance, and the size of the resource constraint k. And generally, we observe that the smaller number 2 and the higher 3 and lower 4 will increase the number of fair models, or the chances of finding a fair model, if you will. And so returning to our initial thought experiment, we think that, given a 10% base rate difference based on our observations, it should be possible if a classifier has good accuracy, i.e. Precision above 75%, it should be feasible to find a fair model that is has precision, false negative rate, and false positive rate between groups within equal within a 5% margin of error. And so we end with a few broader takeaways. Again, the primary one is that slight relaxations in the fairness constraints result in abundant models rather than rare. We also find this kind of more existential idea that seems to be emerging in fair ML literature, which is that accuracy and fairness are actually not necessarily in conflict. Rather, with more accurate models, there's actually more possibilities to satisfy fairness constraints. So the idea here is that more accuracy might actually mean more chances at fairness. And lastly, we close with this idea that achieving fairness along multiple metrics for multiple groups and without sacrificing accuracy is likely more attainable than previously believed. And we encourage the community to kind of keep pursuing this and not give up and think that we should be limited. Perhaps we're self-imposing limits on ourselves with the impossibility result and not thinking about relaxations to these. Thank you. And the team looks forward to any questions you might have. Thanks.